Hi everyone, my name is Jiarun and today I'm going to talk about patch presence test for Java executables. It is a joint work with my colleagues in Fudan University and also Professor Xinyu in Pennsylvania State University. I will first give a brief introduction to the usage scenario of our work. Nowadays, it is very common for software developers or vendors to borrow code from open source projects and integrate them into their closed source products. So there is a serious risk that these undead vulnerabilities would be propagated into closed source software. As we know, undead vulnerabilities are easier to be neutralized by attackers since they could even directly get POCs or exploits. The attack cost of undead vulnerabilities is significantly less than that of 0-day or 1-day vulnerabilities. So in this work, we want to find against undead vulnerabilities, or in other words, the research problem is that how to check whether a closed source software is affected by known vulnerabilities. One effective solution is to check whether a piece of software has applied a security patch for a specific vulnerability. If we could detect the existence of the patch in given software, we could thus confirm its security. This kind of capability is known as patch presence test. It is an important technique to protect software and end users from known threats, and in this work, we present a novel method to achieve this goal. Here are our target users. For example, if you are third-party users of closed source products and also very concerned about the security of the software, you may want a patch presence test tool to help you. Patch presence test is also helpful for developers, testers, and security companies who want to test the given software even without source code. We have summarized several challenges in achieving high precision in patch presence test. First of all, we need to perform source-to-binary analysis in this scenario. What we have is an open source project and piece of code related to specific patches, and what we want is to check the existence of these patches in given executables. So basically, it is hard to perform cross-layer code equivalence test. We need to carefully fill the semantic gaps between source code and bytecode. Second, patches usually introduce small changes to source code. For example, the patch for this vulnerability only moves one line of code. To reliably check the patch presence, we need to consider all meaningful patch changes, which requires fine-grained detection methods. Third, open source projects or libraries are usually customized when integrated into products. Thus, patch presence tests should be resilient to code customization. For example, different vendors have their own versions of Android. Performing patch presence tests on rooms would be hard if we could not carefully deal with customization. Here is the key idea of this work. We present a novel method to directly perform patch presence tests on Java bytecode. We use the word directly since we do not need any additional compiling process to transform the problem into a binary-to-binary analysis, which is usually inflexible in real practice. On the contrary, we extract cross-level features from source-level patches and binary-level smiley code, and further perform a novel matching technique based on these features. Selected features including, for example, constant values, method invocations, field access, and special instruction types. The fine-grained matching techniques provide BScout the capability of effectively recognize the slight changes introduced by a security patch. We do all feature extracting and matching on line level so that we could carefully catch these changes. This idea is straightforward on source code analysis, but how can we introduce this kind of line-level analysis on binary or smiley code in our scenario? In general, we rely on learning-based line segmentation to group smiley instructions into blocks, and we call this kind of blocks as smiley lines. Basically, we want to infer which instructions may belong to the same source line, and then group them together for feature extracting. Another important side of BScout is neutralizing both pre-patch and post-patch source code to neutralize customization. Thus, we could only consider patch-related code changes in matching process. Our key idea is is inspired by the lessons learned from patch presence test at source level. That is, checking how many patch changed lines could be found in the source code. Similarly, we can give patch presence test results on Java executables by checking how many patch changed lines can be found in the target executables. The challenge is that we could not simply adopt a uniform presence test strategy for them. We introduced different detection methods for different kinds of patch changed lines. We define 3 kinds of code changes, including addition line, deletion line, and modification line. So here is the workflow of our approach. After performing line segmentation and cross-level feature extracting, we then do line-level analysis on both pre-patch and post-patch source code to neutralize customization. And finally, we determine the patch presence test result by comparing the patch diff with 2 line-to-line maps. Due to limited time, I will not detailedly introduce each part of our design. If you have interest in our work, we can talk about it in question and answer session. In evaluation, we consider both Android rooms and Java apps as our testing targets. For Android rooms, we collect all CVEs reported from August 2015 to July 2019 on Android frameworks, and these rooms are collected from 6 vendors listed below. For Java apps, we consider 15 CVEs for 11 popular Java libraries. There are both Android apps, desktop apps, and server apps in our dataset. It shows that BScout achieves high precision and no false positive on both 2 datasets. To understand the patch application practice in the real world, we apply BScout to perform a large-scale study. Our study is conducted on 150 collected Android framework CVEs with over 2,500 rooms collected from 7 vendors. The first question is that what is the average lag for different vendors to apply a patch? From the figure, we can see that Google proactively applies patches even before announcing the vulnerabilities to the public, while third-party device manufacturers apply security patches relatively slowly. Besides, the patch lags for different phone models from the same vendor vary significantly. The second question is that do vendors patch vulnerabilities for one model but ignore another? The answer is yes. From the figure, we can find that all vendors have ill-managed CVEs and ill-managed models. In other words, all vendors have ever patched a vulnerability on one model but forgot to patch the same vulnerability on another. The third question is that do vendors correctly set security patch level? The security patch level of a room indicates that the room has patched all the vulnerabilities released before or equal to this level. The data shows that there are many ill-managed rooms for both vendors, so there exists some vulnerabilities at a lower patch level unpatched. Also, we want to know which causes a burden for vendors to timely apply patches from an outside view. It seems that vendors do not care much about patch complexity and severity of a vulnerability. While the result shows that code customization do influence the patch behavior of vendors, we shared these results with testing teams in some vendors. They said that customization do increase the difficulty of applying patches, and they show great interest in patch presence test tool like BScout. Thanks for listening, and welcome for questions.